Welcome to the fourth video for the lab torsion and bending on a circular hollow tube. In this one, we'll go through changing our strains from our strain rosettes, the experimental strains, into the principal stresses that those indicate for that point. When using a strain rosette, we need to remember that the equation for the strain in direction, say, A, is going to be equal to the strain in the x direction times the square of the cosine of the angle that A is at, plus the strain in the y direction times the sine squared of the angle that A is at, plus the shear strain times the sine of the angle that A is at times the cosine that the angle A is at for our directions such as this. Now, we're also going to have the same thing for strains in the B and C, and indeed D, E, and F as well. So we're going to have these three simultaneous equations, right? Because we're also going to have the strain at B is going to be equal to the strain in the x direction times the cosine of the angle that B is at squared, plus the strain in the y direction times sine of the angle that B is at squared, plus the shear strain in the xy direction times the sine at the angle B is at times the cosine that angle B is at, and so on for C. So we'll have three simultaneous equations to solve if we want to use this approach. And of course, we're going to want to end up with the stresses from them. And so we're going to want to use that the strain in the x direction is equal to 1 over the Young's modulus times the normal stress in the x direction minus a Poisson's ratio times the normal stress in the y direction minus Poisson's ratio, which we're calling mu in this lab, don't ask me why, times the normal stress in the z direction. But of course, in this lab, we're not going to have any normal stress in the z direction. That goes away. So we're left with only those two terms right there. Similarly, the normal strain in the y direction will be equal to 1 over the Young's modulus times the normal stress in the y direction minus Poisson times the normal stress in the x direction. And we just won't have anything for the z direction. It would be present, but it's the stress is 0. You know that. And then we'll also have that the shear strain is equal to 1 over our shear modulus times the shear stress. We do have a way of relating the shear modulus to the Young's modulus, so we can rewrite this as 1 over the Young's modulus times 2 times 1 plus the Poisson's ratio times the shear stress. Let's draw a line between those. So we can use those to get from our strains to our stresses if we if we want to rearrange them, or to get from our theoretical stresses to our theoretical strains. So when we're trying to calculate our strains in the x, y, and y direction, and our shear strain, and then we can use that to convert to find our principal stresses, which we already talked about. We're going to need to solve 3 of those simultaneously. Now that's kind of a pain in the neck, but we can use linear algebra to make things a lot easier. So we're looking at these right here. We've got it all worked out. We can use our directional matrix, our constitutive matrix, and we can use linear algebra to solve this. So it is a true fact that if we use our if we define our shear, our strain vector as just the strain at A, strain at B, and the strain at C, and then we identify our second strain vector in the x and y direction as the strain in the x direction, the strain in the y direction, and the strain in the x, y direction. And then our stresses, we define that. Our stress vector is just equal to the stress in the x direction, the stress in the y direction, and the shear stress in the xy direction. And then we define our directional vector, our directional matrix. Now, this is going to look like an awful lot of work, but you can probably do it pretty easily, I would say, especially if you have access to MATLAB right now. It's just going to be the square, your cosine, A, the sine, your cosine, A, and then your sine of your theta A. Square that times the cosine of theta A. This should remind some of you who, if you haven't taken linear algebra yet or any sort of matrix classes, should remind you of when I talk about how much I love using Gaussian elimination. We can do the same thing for this second row for B and this theta. So cosine squared theta B, sine squared, and I should put commas here so that you can see that these two are one term. Sine squared theta B, sine theta B, cosine theta B, and then finally for C, we can do the exact same thing. And this looks like a real pain in the neck, but remember, these are all constants. So this matrix that looks big and ugly, it's going to end up being some pretty simple constants. So no big deal. Sine angle C, cosine angle C. And then for converting from normal stresses and shear stresses into strains, we're going to have our constitutive matrix C. Which is going to be 1 of the Young's modulus, and then 1, and then negative Poisson, 1, because the normal stress in the x direction is 1 over E, and then negative Poisson over E for the normal stress in the other direction, and then 0, of course, for the shear stress. And then again 0 right here, 0, 0, and then converting into the shear modulus from the Young's modulus. So we obtain 2, 1 plus Poisson, which is the stuff between them. We can also invert this to convert from strains into stresses. It's very, very similar. So now, if we want to write out all of these equations from these top ones, I only did the first 2, but there's a third one. It looks exactly the same except for with C's instead of B's or A's. We can just write this matrix is equal to, or this vector is equal to this matrix, I guess, times this vector right here. Which is pretty easy to do if you have access to MATLAB or even your graphing calculators. And similarly, we can solve for these equations to go from our strains to our stresses using this and this is a matrix, and this is a vector. So that'll be quite easy to execute, assuming that you have the ability to do linear algebra mechanically. So it's a lot of fun to do this, and it's the sort of thing that you'll do in other more advanced engineering courses. So I hope you enjoy it. Now on to looking at the curves that we're going to be graphing. We want all these curves on one graph, so that's the next video though.